In this video, we'll be looking at using the method of Lagrange multipliers to solve optimization problems given constraints. Here we're trying to minimize z, which is a function of x and y equals x squared plus y squared, given the constraint 2x plus 4y equals 5. And the method the of Lagrange multipliers is that if you're given a function you're trying to maximize or optimize and a constraint function, then the gradient of the objective function is equal to a multiple of the gradient of the constraint function. And then you can set up this system of equations. Here we know what our objective function is. Our constraint function is this 2x plus 4y equals 5. So that is going to be our g of xy is equal to 2x plus 4y equals 5. So if the gradients are parallel, then the components of the gradients are scalar multiples. So the partial derivative of this f of xy function with respect to x, that's going to be our 2x. That has to equal, we just found this using this here, that has to equal a multiple of the partial derivative of the g function with respect to x. So 2x is equal to lambda times 2. Now our second equation that we're going to come up with is using the partial derivatives with respect to y. The derivative of this with respect to y is our 2y, and the partial derivative of our constraint with respect to y is 4. So that's going to be a multiple times 4. And then our constraint function itself is 2x plus 4y equals 5. Here we have a system of three equations with three variables. We want to find the values for x and y that will minimize this function. Alright, so what we can see right away from the first equation is that if you divide both of these by 2, you can see that x is equal to lambda. If you divide the second equation by 2, you can see that y is equal to 2 lambda. And when we plug that into the third equation, it's going to be 2 times our value for x, which is lambda, plus 4 times the value for y, which is 2 lambda, has to equal 5. When we simplify this, we get 2 lambda plus 8 lambda is equal to 5. So 10 lambda equals 5, and that means lambda is equal to 5 over 10, or 1/2. So that's our value for lambda, and that now we can plug that back into these equations here and here to find x. X is equal to lambda, so x has to equal 1/2. Y is equal to 2 times lambda, so 2 times 1/2 is 1. So this is our critical point there that is going to optimize the function with the given constraint. Now to find the minimum value of this, we're going to plug this into our original f of xy. Since f of xy, we started off with f of xy was x squared plus y squared. We're going to evaluate that to find the minimum. We're going to evaluate it at the point where x is 1/2 and y is equal to 1. So that's going to be 1/2 quantity squared plus 1 squared. So that is going to be 1/4 plus 1, and that is 5 over 4. So this ends up being the the minimum of this function of two variables given the constraint. If you choose any other points in the domain, all of those other points are going to be greater than 5/4. This is the minimum of the function of those two variables. Okay, for this example, again, we want to minimize this with the given constraint. Okay, let's minimize f of xy equals x squared minus 10x plus y squared minus 14y plus 28, given the constraint that x plus y equals 6. You can set up your system of equations. You can find three equations with the three variables x, y, and lambda. You have your function, your objective function you're trying to maximize. That's your f of xy. And then your constraint equation is x plus y equals 6. We're going to let g of xy be our constraint for x plus y equals 6. Now we can set those partial derivatives to be equal. The partial derivative with respect to x is 2x minus 10. Okay, and we treat the y's as constant, so the rest of that is equal to 0. That has to equal the partial derivative of the g function with respect to x times that lambda multiplier. So that's going to equal lambda times the partial derivative of this with respect to x, and that's going to be 1. So 2x minus 10 equals lambda. Get rid of that. Now, take the partial derivative with respect to y. The partial derivative of our f of xy function with respect to y, we treat y as a variable and treat x as a constant. And that is going to be the partial derivative of this with respect to y is going to be 2y minus 14. And that's going to equal the multiplier of the partial derivative of this g function with respect to y, which is also 1. Again, what I'm doing here is taking the partial derivative with respect to x of the f of xy function and setting that equal to the multiplier times the partial derivative of with respect to x of the g of xy function. And then that's our first one, and this one we just calculated with that. And then the way we get our third equation is to just rewrite the constraint equation, x plus y is equal to 6. So we have our 1, 2, 3 equations here, 3 variables, and we want to solve this system of equations. Okay, one way of doing this is to solve for x in the first equation, solve for y in the second equation, and then substitute both of those into the third equation. When you solve for x, you add 10 to both sides, you get 2x equals lambda plus 10, and then when you divide by 2, you get x is equal to the lambda plus 10 all divided by 2, or lambda divided by 2 plus 10 divided by 2, which is 5. When you solve the second equation for y, you can add 14 to both sides to get 2y equals lambda plus 14. And then when you divide by 2, you get lambda divided by 2 plus 14 divided by 2, which is 7. Now what we're going to do is take this x and y and substitute it in to the x and y in that third equation so that we end up with an equation that has just the lambda. And we're going to solve for lambda. So if x is lambda over 2 plus 5, that's our x, plus y is lambda over 2 plus 7, that has to equal 6. Now when we simplify this, a lambda over 2 plus a lambda over 2, we get lambda, and then 5 plus 7, we get 12 equals 6. So lambda plus 12 equals 6, and then we can solve this for lambda and find that lambda is equal to negative 6. Now we're going to take our solution here for lambda and plug it into here and here. So when we plug that in, we can find that x is equal to lambda, which is negative 6 divided by 2 plus 5, and we get x is equal to negative 6 divided by 2 is negative 3 plus 5 is equal to 2. Now when we let lambda equal negative 6 for the y equation, we get y is equal to negative 6 over 2 plus 7. So that's going to be negative 3 plus 7, and we get y is equal to 4. So we have found the values, those critical values for x and y. being 2 and 4. Now we're going to plug that into the objective equation, the function that you're trying to maximize or minimize. So we want to evaluate f of 2 comma 4. And you're going to take those values we got for x and y and plug it back into this f of xy function. You're plugging in 2 for x. It's going to be 2 squared minus 10 times 2 plus y squared when y is 4. 4 squared minus 14 times 4 plus 28. And then that will all simplify to negative 28. So that's going to be the minimum of that function with the given constraint. Okay, for this last example, we want to find 3 integers whose product is 125 with a minimum sum. We're not given explicitly the 2 functions, the function we're trying to maximize and the constraint function, but we can certainly come up with that. So, all right, we have what we're trying to maximize or minimize here is the sum. The sum of 3 numbers. Well, 3 numbers, we can let x, y, and z be those 3 numbers. Then you can say that the sum is what you're trying to maximize. The sum is going to be our f of x, y, z. Okay. We have this formula here for the Lagrange multipliers for a function of 2 variables, but we can certainly extend that to a function of 3 variables. So the sum of those 3 integers is going to be x plus y plus z. So that's our objective equation. That's what we're trying to minimize. And the constraint, that's going to be our g of xy. In fact, it's going to be our g of x, y, and z, is going to be that the product of those 3 numbers has to be 125. So the product is when you multiply x times y times z has to equal 125. Again, what we have here, our sum is our objective equation. That's what we're trying to minimize, the sum. And then this other equation, which was the product, that is our constraint equation. So we have our f of xyz and our g of xyz. Now, when we have this as a function of 3 variables, we need to extend this so that we're also looking at the partial derivatives with respect to z. Okay, by using the definition in the method of Lagrange multipliers, the gradient of the f of xyz function has to equal a multiple of the gradient of the g of xyz function. So that means the partial derivative with respect to x of the xyz function has to equal that scalar multiple of the partial derivative of g with respect to x of that xyz function. The partial derivative with respect to y of that function has to equal a multiple of the partial derivative with respect to y of the constraint function. And then the partial derivative with respect to z of our xyz has to equal a multiple of the partial derivative with respect to z of your constraint equation. So we are extending that to a function of 3 variables. The gradients are still going to be parallel. So when we find those partial derivatives and set them to be equal, the partial derivative of our objective function with respect to x, that is going to be 1. Treat x as a variable, y is z as constant. That has to equal a multiple times the partial derivative of our constraint with respect to x. Treat x as a variable and y and z are constant, so that's going to be 1 is equal to y times z. Take the partial derivative of the objective function with respect to y, and that partial derivative is going to be 1. That's going to equal a multiple of our partial derivative with respect to y of our constraint. Treat y as a variable and x and z as constants. And then the partial derivative with respect to z is the derivative here with respect to z is 1, and that is going to equal a multiple lambda times the partial derivative with respect to z. Treat z as the variable and x and y as constants. So we have these 3 equations as well as our constraint equation. So we have 4 equations with 4 unknowns. So we have these 3 equations as well as the equation x, y, z has to equal 125. Now what I would recommend here is that if we were to solve this by dividing by lambda, take the first equation and divide by lambda and look at what we get. Okay, so 1 over lambda, actually I'm going to pause, start this on a new page. Now if we divide the first equation, again I just copied this from the previous page here, if we divide by lambda, notice that we get 1 over lambda is equal to y times z. And if you divide the second equation by lambda, you get 1 over lambda is equal to x times z. Divide the third equation by lambda, you get 1 over lambda is equal to x times y. Well, if 1 over lambda is the same as this 1 over lambda, then by combining these first 2 equations, since these are both equal, then y times z has to equal x times z. And if y times z has to equal x times z, and if you divide both sides by z, you can see that y has to equal x by combining those first 2 equations, since they're both equal to 1 over lambda. By combining the second and the third equation, if this 1 over lambda is equal to this 1 over lambda, then this x times z has to equal this x times y. If you divide both of these by x, you'll see that z has to equal y. So if x equals y and y equals z, then x, y, and z must all be the same value. So if we can say that, then x is equal to y, and y is equal to z, then x and y and z are all equal. So let's plug that into that constraint equation to find the value for x, y, and z. If we replace what y is equal to x, and z is equal to x, then you get the equation x to the third is equal to 125. Take the cubed root of both sides to get x is equal to 5. So if x is equal to 5, that means y is equal to 5 and z is equal to 5. And again, the function that we were trying to maximize, minimize the sum. We're trying to minimize the sum equation. The sum was our f of x, y, z, which was equal to x plus y plus z. And if we evaluate that for our critical point here, when x is 5, y is 5, and z is 5, we see that the minimum sum of 3 numbers whose product is 125, sorry, wrong, that sum is 15. So this is the minimum sum of 3 numbers whose product is equal to 125.